Have you ever looked up at the night sky, mesmerized by the countless stars, and wondered where it all came from? What were the conditions that allowed for such a breathtaking display of cosmic beauty? To truly understand our present universe with all its complexity and wonder, we have to journey back. We must embark on a voyage through time, 13.8 billion years, to the universe's very first moments, to the genesis of everything we know. This isn't a journey by spaceship, a physical voyage across the vast cosmos, but a journey of the mind, a quest for knowledge guided by the principles of science and the power of human curiosity. We're cosmic detectives, meticulously gathering evidence from the distant past, piecing together clues like fragments of an ancient puzzle, from a time long gone, almost beyond comprehension. The universe began in unimaginable heat and density, a state far removed from the cold, empty space we observe today. A singularity, a point of pure energy, the ultimate source of all that exists. In the first microsecond after the Big Bang, a period of time so short it's almost impossible to grasp, the fundamental rules of physics, the very laws that govern our universe were just taking shape. To understand these forces, to unravel their mysteries, we strive to recreate that primordial fire, those extreme conditions right here on Earth, in our laboratories. Why? What drives us to pursue such ambitious and challenging experiments? Because those first moments, that fleeting instant of creation, hold the answers to some of the biggest questions that humanity has ever pondered. Why is there matter at all? Why is there something rather than nothing? How did everything, from the smallest particles to the largest galaxies, emerge from the initial chaos? By meticulously simulating these extreme conditions, by recreating the early universe in miniature, we can rigorously test our deepest theories about the nature of reality, pushing the boundaries of human knowledge. This quest, this relentless pursuit of understanding, requires some of the most complex and sophisticated machines ever built by humankind. Every single atom in your body, the very building blocks of your being, was forged in the heart of stars, in processes that began in that initial inferno of the Big Bang. Therefore, understanding the early universe, deciphering its secrets, is ultimately understanding our own origins, our place in the grand cosmic tapestry. So, driven by this profound desire to know, we build these magnificent machines, these technological marvels, to glimpse for a brief instant the dawn of time, to witness how it all began, and to understand our connection to the cosmos. Imagine trying to journey back to the very beginning of time. How do you build a time machine, a portal to the past? How do you engineer an experiment to visit, even for a fleeting moment, the first microsecond of creation, when the universe was in its infancy? The answer, perhaps surprisingly, lies in the heart of physics. You need a particle accelerator. Think of these incredible machines as colossal racetracks, but instead of cars, they're designed for the tiniest bits of matter imaginable. The Large Hadron Collider at CERN, a marvel of engineering, and the Relativistic Heavy Ion Collider in the US, are the world's most powerful instruments for this purpose. They are the world's most powerful tools for recreating the universe's earliest moments. Scientists begin by stripping heavy atomic nuclei of their electrons, preparing them for their high-speed journey. These nuclei are then injected into miles-long tunnels, vast underground pathways. Superconducting magnets cooled to temperatures colder than deep space, far below freezing, precisely guide the particles, keeping them on track. Then, electric fields accelerate them, pushing them faster and faster to nearly the speed of light. The grand finale, a carefully orchestrated series of head-on collisions of these incredibly fast-moving nuclei. The impact releases an immense amount of energy in a space smaller than a proton, reaching temperatures over 4 trillion degrees Celsius, hotter than anything else in the known universe. For a fleeting moment, a mere fraction of a second, we recreate in miniature the extreme conditions of the early universe. These collisions shatter matter, obliterating its familiar forms. They break it down into its most fundamental components, the very building blocks of reality. By smashing things apart with incredible force, we reveal what's inside, uncovering the secrets of matter itself. We witness the raw, untamed state of the cosmos, a glimpse into the universe's earliest days. We see the universe as it was before atoms existed, a primordial soup of energy and particles. It's a violent, beautiful, and profoundly informative process, offering invaluable insights into the nature of reality. Deep within the heart of matter, a fascinating phenomenon awaits. When heavy nuclei like gold or lead collide at near-light speed, protons and neutrons, The building blocks of atomic nuclei momentarily dissolve, losing their individual identities. This dissolution releases their inner constituents, the fundamental particles that make them up. These particles are unleashed into a fleeting, exotic state called quark-gluon plasma, or QGP. It's a state of matter unlike anything we encounter in our everyday lives. In our familiar world, quarks are permanently locked inside protons and neutrons, never seen in isolation. They are tightly bound by gluons, the carriers of the strong nuclear force, which is the strongest force in nature. But in the extreme heat generated within the collider, those powerful bonds break. The strong nuclear force is overcome. Quarks and gluons, once confined, now roam free, creating a sea of fundamental particles. This results in a dense, liquid-like plasma, a superheated soup of quarks and gluons. This exotic state mirrors the conditions that existed in the very early universe, in its first few microseconds after the Big Bang, a time when the universe was unimaginably hot and dense. Before the formation of any atoms, just a perfect fluid of free quarks and gluons filled all of space. Recreating this quark-gluon plasma in the lab is akin to finding a fossil of the Big Bang, allowing us to probe the universe's earliest moments. It lets us study matter and its fundamental interactions under extreme conditions found nowhere else in the present-day universe. The behavior of the QGP is governed by the theory of quantum chromodynamics, or QCD, but its complex equations are notoriously tough to solve analytically. Experiments at particle colliders have surprisingly shown that the plasma behaves like a nearly perfect fluid, with almost no viscosity, rather than a weakly interacting gas of particles. By meticulously studying its properties, such as its temperature, density, and flow patterns, we gain invaluable insights into how the cosmos transitioned from its primordial state to the universe we observe today. It's a direct link to our cosmic origins, a window into the very moment before matter, as we know it, came into existence. Creating quark-gluon plasma is just the beginning. As the fireball expands and cools, a dramatic transformation occurs. Quarks and gluons are recaptured by the strong force. This process, called hadronization, forms protons, neutrons, and a zoo of exotic particles. Sophisticated detectors track thousands of these new particles as they fly out from the collision. By analyzing their patterns, scientists reconstruct what happened inside the plasma. We witness in real time the transition from fundamental freedom to confinement, the birth of matter. This is how the universe went from a simple soup to the complex cosmos we see today. Every proton is a relic of this cosmic phase transition. Studying hadronization in the lab lets us witness the creation story of matter itself. To probe the quark-gluon plasma, scientists use heavy quarks as cosmic spies. In high-energy collisions, charm and bottom quarks are created early, right when the plasma is hottest. These heavyweights aren't easily pushed around. They travel through the plasma, losing energy slowly. By measuring their paths and energy loss, we map the plasma's properties. Researchers analyze how hadrons containing heavy quarks interact with lighter particles. The flow patterns reveal the plasma's viscosity and density. Heavy quarks are calibrated probes. Any change in them tells us about their journey. They're our messengers from the heart of the fire, carrying information about the universe's first moments. For years, models focused on the hottest phase, the quark-gluon plasma. But as the plasma cools, there's a crucial in-between phase, a mix of deconfined quarks and forming hadrons. Ignoring this is like skipping the final chapters of a book. Heavy quarks continue to interact with new particles during this cooling, altering their energy and path. To truly understand the plasma, we must account for this transition. New models now include these interactions, giving a more accurate picture from collision to detection. This holistic view is changing how we interpret data from the LHC and RHIC. Science advances as new data refines our models, bringing us closer to the universe's true birth story. The LHC and RHIC have opened a window into the dawn of time, but the journey continues. Next-generation experiments will probe the strong force with even greater precision. By lowering energies, we can create denser matter and map the full phase diagram of nuclear matter. Facilities like CERN's SPS and Germany's FAIR will explore new frontiers, including matter like that in neutron stars. These experiments will complement high-temperature studies, giving a complete picture of matter's behavior. We aim to pinpoint the transition from hadronic matter to quark-gluon plasma and search for new states of matter. Each discovery builds a more robust model of the early universe. This research connects us to our cosmic origins, reminding us we're made of the cooled embers of a quark-gluon plasma. The quest continues.